In this episode, I'm going to talk about infinitely repeated games. Well, what does that mean? That means the horizon of the game is infinite. So there is no final stage game. There's no end to the game. The game will continue forever. Once again, it doesn't sound realistic. It isn't. But we just use those games to picture environments where players do not foresee any immediate end or sort of foreseeable end to the game. All right, well, obviously this brings some technical issues. For example, what is going to be happening to the payoffs? Well, if you think of a payoff, for example, t from 0 to infinity, ui at, so delta to the power t. Well, here, the question is this going to be a bounded payoff, right? I mean, today I'm going to get payoff 2, tomorrow 3, and then 3 periods later 4, 5. So it's like, a bunch of positive numbers. When I add them up, may I actually ending up some sort of infinite number? Because, I mean, a huge number. Well, probably it's going to be huge, right? Because it's an infinite horizon. But thanks God, because this delta is very, in between 0 and 1, the payoffs will be bounded, all right? Meaning it is not going to diverge to infinity, all right? So therefore, this delta is actually very, very important parameter in the payoff calculation, so that the total payoff in this repeated game does not blow to infinity. All right, so it's going to be bounded. Well, the other problem is, how am I going to use backward induction? Because there's no final stage or final period. How can I build up my SP&E? Well, remember the one deviation property. This is exactly what we are going to use. So in games, well, the version of the theorem, one deviation property we described, was true for finite horizon extensive form games, but this is infinite horizon. But a similar version of this one deviation property we described in our earlier videos holds if the payoff in an infinite horizon game is bounded. So therefore, for our infinite horizon repeated games, we can actually use one deviation property. Well, again, for the details, please go back to this video. But in a nutshell, the idea was the following. You do not have to, build up SP&E from the final subgame, because there is no such subgame in this game, infinite horizon repeated game. But what you can use is that, given a strategy profile, strategy of each player, if you want to check whether this is an SP&E or not, what you have to do for any player and after any history, right? Remember, every history defines a subgame. What you should check is the following. So for any history, look at the players. So history that follows player one's move. All right. So look at player one's move. Does he have incentive to deviate? Well, but there might be a bunch of different deviations, right? He can deviate in this period, and then in the next period, or maybe 10 more periods, and then he may actually not deviate, sort of play according to this strategy. Well, the one deviation property says, look only at one deviation in this period deviation, so periods t plus 1. So given a history of length t, look at the deviation in periods t plus 1, all right? Well, what about for the rest of the game? For the rest of the game, let's assume these players are going to stick to their strategies, all right? So the player deviates only in periods t plus 1. He does something else, something different than what he's supposed to do. But for the rest of the game, all the players are going to play according to their strategies. So given that there is no profitable such deviation, and if this is true for each player and for every history, well then, you know what? That strategy profile forms an SP&E. All right, so that's basically the rough idea. Well, normally, obviously, there might be infinitely many possible strategies, but the trigger strategies are normally and usually SP&E for high enough delta, right? For high enough delta. So the patience is important for our sort of SP needs. If the players are not patient, well, unfortunately, not a lot of strategies will be SPNE, because they, again, look at the most extreme case where delta is equal to 0. So the players are completely impatient. The only thing they care is today. So therefore, the only SPNE in this game is going to be the stage game Nash equilibrium, right? Okay, so, but the thing is, if delta is high enough, we can support a lot of strategies and a lot of payoffs as an SPNE. And the trigger strategies are widely used strategies. So what do they look like? Well, usually the trigger strategies consist of several action profiles. Usually 2 is enough, but sometimes more than 2 is might be necessary. One profile is usually called cooperative profile. All right. So they cooperate to achieve that profile. Usually that profile is not Nash equilibrium. All right. So we call it cooperative profile probably because although it's not Nash, it gives both players a higher payoff. Well, then there's the second group of profiles is called punishment profile. Well, what is the role of those punishment profile? Is basically if they do not play cooperative profile strategies, well, they're going to switch to punishment profile and they're going to keep playing this forever. And usually the punishment profile strategies are Nash equilibrium off the stage game. And the trigger strategies usually work in the following way. The game starts with players playing cooperative profile actions. All right? And every period they're going to play the cooperative profile unless they see that one or maybe more than one player deviates. So if anybody deviates, all right, well then all the players move to punishment profile, meaning they play the punishment profile strategies for the rest of the game forever. All right. So that's basically the idea of trigger strategies, or the strategy that I just described to you is usually called Grimm trigger strategy. So those strategies are most like carrot and stick type of behaviors that we observe in real life. It's like so let me give a more concrete example. So the prisoner's dilemma, once again, because it has a unique Nash equilibrium. But the Nash equilibrium is inefficient. So cooperate, deviate, cooperate, deviate. So cooperation is going to bring each player 2 and 2 payoff. But the thing is, it's not a Nash equilibrium because given that one party cooperates, the other party has a huge incentive to deviate. So 0, 4, 4, 0. And they actually end up playing DD. And by the way, in this game, D and D is a strictly dominant strategy. All right, so the C, the action, the strategy C is strictly dominated. So the only Nash equilibrium of this stage game is D and D, where both player gets payoff of 1. But the question is, can these guys achieve a payoff 2 and 2 at each period? Meaning, can they play CC forever? Can this be a subgame perfect Nash equilibrium outcome? Well, the answer is yes, it can be subgame perfect Nash equilibrium outcome. But how? Well, here is the Grimm trigger strategy. Players start playing CC. Well, by which I mean in period, at the very beginning of the game, player 1 is going to play C, player 2 is going to play C. All right? For the rest of the game, they will play, CC unless, let's put it this way, if nobody plays D, all right, D before. So in period 0, if they both play C and C, in period 1, they will play C and C. Well, because they played C and C in both period 0 and 1, in period 2, they will play C and C. All right, so in period 100, they will play C and C if nobody before, all right, if nobody before played D. All right, so basically this is the cooperative profile, the cooperation stage. However, right, somebody may have deviated. If one or two players ever play D, so maybe player 1 plays D at some round, or maybe player 2, or maybe both play D, right? Well, if that happens, well then the players are going to play D and D forever. So here's one thing I would like to say is like, we cannot really be too formal in terms of describing strategies in an infinite horizon repeated game, because the strategy, remember, the definition of strategy was at every decision node we should tell what each player is going to do. Well, here in an infinite horizon game, there are infinitely many possible decision node for each player. So a strategy profile is going to be like a huge, very complicated animal. So it's like trying to be too formal about it doesn't really make much sense. So what do? We verbally define it. Well, but nevertheless, one thing that is very, very critical, you have to cover all possible histories of the game. And so tell us what the players are going to do. All right, so that description should tell me what players are going to do after any possible history. So here, the thing is, they may play CC, CC, CC. All right, so CC. So in that case, we know what the next period will be. It's going to be CC. But the thing is, it might be, for example, CC in period 1 and then CD in period 2, right? This is one possible history. So the thing is, CC, CD. What's going to happen here? Well, I know that according to those strategies, it's going to be DD forever, right? Good. What if it was CC, 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 and then all of a sudden DD? Well, I know that for the rest of the game, it's going to be DD, right? So therefore, the next stage move is going to be C and C for both players if you observe nothing but C. However, in any period, if you observe D by any player, well, then you know what? The rest of the game, forever, they're going to play D and D. All right, so that's the agreement. So this play DD is a punishment profile. And as you see, by the way, DD is a Nash equilibrium of this game. So therefore, playing DD forever, all right? So regardless of the history, playing DD forever is basically a Nash equilibrium in that subgame. Remember our earlier result? Repeating the Nash equilibrium of a game is an SPNE, or therefore it's a Nash equilibrium in any subgame. So this is DD is a Nash equilibrium. Very good. But what we have to check is playing CC, can we support it as a Nash equilibrium of this entire game? So therefore this strategy profile is SPNE. Well, we can if the discount factor is large enough. Well, what is the thing? How can we guarantee this? How do we check this? Well, simple. You first check no deviation payoff. Oh, well, you have to do it for player 1 and obviously for player 2. But here I'm going to do it only for player 1 because the payoffs are symmetric, strategies are symmetric, and therefore once I get some inequality about delta, it will be exactly the same inequality for player 2 because everything is symmetric. All right? So, but you have to do it for all the players. So for player 1, I'm going to calculate his no deviation payoff. And then I'm going to calculate his deviation payoff. So the nice thing is that here, there's only one deviation, right? I mean, normally your strategy tells me to play C, and so if you want to deviate, well, again, one deviation property is like we allow players to deviate only in one stage. Well, there's only one thing that you can do. It's like deviating to D. So therefore, the deviation payoff is going to be, well, what if player 1 deviates to D? All right. So, and then compare these two. Well, no deviation payoff should be greater than or equal to the deviation payoff. So therefore, the no deviation, the strategies that described here actually best responds the other guy's strategy. So what is the no deviation payoff here? Well, in which period are we talking about? Well, that's the nice thing about repeated games, infinite horizon repeated games, and those strategies. It doesn't matter because here, remember, the nice thing is that as long as players played CC before, well, whether this is period 10 or 100 or 1000, doesn't matter because the rest of the game is exactly the same, right? I mean, they will keep playing this game again and again forever. And so therefore, you can think of this, we do this analysis for any period, all right? For any period where we observed no deviation before. Well, you may ask, what if the same analysis for histories where deviation occurred? Well, remember, in those subgames, according to those Grim Trigger strategies, players are going to play DD forever. And we know that this is a Nash equilibrium of these subgames because repeating the stage game Nash is always a Nash of the subgame, or you see what I mean? All right, so therefore, if player 1 does not deviate, well, his entire game payoff is going to be what? Well, he's going to get, remember, 2 in period 0, well, or in period that we started. But let's suppose, without loss of generality, this is period 0. And then he gets another 2 a period later, and so it's 2 delta. And then another 2 in 2 periods later, so 2 delta square, and so on. Well, the nice thing about it, we can actually simplify this as 2 parentheses 1 plus delta square, etc., all the way to sort of forever. Well, and the nice thing about this is a geometric sum because delta is less than 1 and greater than 0. This is actually equal to 2 divided by 1 minus delta. Well, what about the deviation payoff? All right, so again, one deviation. So player 1 deviates to D. Well, what about player 2? Player 2, remember, we fix his strategy. He's playing C in this period. So therefore, by this deviation, player 1 is going to get 4 payoff. Good. So there's no delta because this is what exactly he's going to get in this period. Next period, well, so this is the trick of the one deviation property. We allow just one deviation, one period deviation, and then assume that players are going to play according to their strategies for the rest of the game. So is it going to be 2 delta plus 2 delta square, etc.? No. Why? Well, look at those strategy profiles. It says, look, these guys are going to play CC if nobody before played D, but here player 1 actually plays D, and so he changes the history of this game. And therefore, the strategies are going to react to that. How? Well, they're going to play D for the rest of the game. All right? So by deviating, you trigger punishment. This is why we call it trigger strategies. So by deviating, player 1 is triggering the punishment, so that means they're going to play DD forever, which means 1 times delta plus 1 times delta square plus 1 times delta cube, and so on. It goes like forever. So one thing you may wonder, well, I'm the player 1, I deviate today, and I know my opponent is going to start punishing me tomorrow. But why don't I deviate next round as well? Well, I mean, you can try. Remember, if you know that your opponent is going to start punishing you and therefore playing D, the best action for you is to play D because DD is the Nash equilibrium. So therefore, if you try to deviate in the second period as well, the best you're going to get is 0, which is worse than 1. So there's no point in deviating in next period and next period. This is actually why the one deviation property works. Also given the fact that playing DD is a Nash equilibrium. And this is exactly why we use the punishment profile as the Nash equilibrium strategy profile. All right? So we know that deviating more than one period is not going to be profitable for you. So you can deviate only just one period. All right, so this is the deviation payoff. What is it equal to? Well, that's simple. This is 4 plus, taking it to delta parentheses, it's going to be 1 plus delta square plus forever. And so this is equal to 1 divided by 1 minus delta. So this payoff is equal to 4 plus delta divided by 1 minus delta. The question is, when this guy is greater than or equal to this guy. So the no deviation is greater than or equal to the deviation payoff. So if deviation payoff is greater, that means these guys actually are going to deviate even at the very beginning of the game. So therefore these strategies cannot be subgame perfect Nash. So when 2 plus 1 minus delta greater than or equal to 4 plus, let me erase this part. This is 4 plus delta divided by 1 minus delta, right? Well, multiply both sides by 1 minus delta. I know it's positive, so it's not going to change the inequality. So I'm going to get 2 greater than or equal to 4 minus 4 delta plus delta. So I have here, I have 2 on the right-hand side. I have minus 3 delta, but I send it to the other side as 3 delta. So you know what? As delta greater than or equal to 2 over 3, the no deviation payoff is going to be greater than or equal to deviation payoff. Hence, this strategy is SPNE if delta is greater than or equal to 2 divided by 3. That's it. I don't really need to check anything else. Once again, we know this is a very complicated extensive form games, but the trick that the punishment profile is a Nash equilibrium and the punishment is playing DD forever. And so any subgame that follows some player playing D is actually, those strategies are going to form a Nash equilibrium. And then, so the history that we should check is that a history where no deviation ever occurred. And then in this history, we already know that deviation is not going to benefit this agent because he's patient enough. So therefore, as long as delta is greater than or equal to 2/3, those strategies, this Grim trigger strategy is the SPNE of this game. All right? Question is, are there any other SPNE in this game? Yes, there are many. Well, here, according to this, we actually support on the equilibrium path what payoff? We support 2 divided by 1 minus delta. If delta is very close to 1, by the way, this is a very large number, right? As delta goes to 1, this thing goes to infinity. But remember, we assume delta is less than 1. So this may be very huge. But the thing is, what we normally look at is the average payoff. Average payoff. What does that mean? That means we basically multiply the payoff by 1 minus delta. All right? And so this is the average. So on average, what is the payoff they're going to get here? It's 2, right? Each player is going to get 2 forever. The question is, maybe they're going to play CC sometimes and CD sometimes. Can this be a Nash equilibrium? Subgame perfect Nash? Not according to these strategies, according to some other strategy. Yes, it is possible. And so, question is, in this game where the Nash equilibrium, a unique Nash equilibrium is strictly dominant strategy and it's inefficient, but what we saw is that an efficient outcome can be supported as a subgame perfect Nash equilibrium outcome of this game if the players are patient enough and if this game is repeated infinite horizon. The question is that it? Can we support any other average payoff? Average here, again, Maybe sometimes they're going to play CC, but sometimes maybe they're going to get DC or CD. So you see what I mean? They're going to get something more than 2. Is it possible? So that's what we are going to answer next.